because I know this has been prepared for you only. Any type of difficulty, please come forward immediately. Nothing very high I am going to talk. You know everything. Only thing, how these things which you know is put in the word known as modeling. That's all I have done. Nothing else. You know everything. So please do not hesitate in stopping me anywhere, anytime. See, I have written 2-3 lines here. What it says, what you understand for the model. So this is model. You are making a model. Somebody says you are making a model. What for you are making a model? A model of the car, a model of the helicopter, anything. That way, I am going to synonymize the word modeling. What is the meaning of the modeling? So what I said is, modeling is just miniaturized representation of anything. A small representation, very small representation of anything. A system, it can be a device, it can be a system. Alright? Then we said imitation. You try to imitate me also in the class. After the class, some students of mine try to imitate my words also, my action also. That is also model. Then we say anything, any item you take. How this consists of, how it has been composed of, what type of model is there. We say one body center, cubic center, say tetrahedron. So what type of representation? One atom looks like this. Then if these atoms make the body, make the system, how does it look like? That will be miniaturized model. System or the postulates of the systems all come in the same way. So what we say, the device behavior can be any device you take. Device is what? You put something, you get something other than what you put in. That depends on the characteristic of the device. Now device is what? So what we say is the device behavior. If I can predict the device behavior, that is what the model. I have a device. The characteristic of the device, something is known to me, and then I can say the device will behave like this. Alright? So it can be in the form of the device we write. Anything you write. A diode is there. You write something. What is that? Unidirectional. So much is the current limit. So much is the voltage. You write it. Or you put it in a sketch form. Some drawings. That means these different types of sketches, drawings, physical presentation, writings, is all known as language. So we can put this in different language. Modeling is, can put in the different language, can be done in several languages. What is languages? Drawing you are putting, sketches you are putting, writing you are putting, these all are language. In one language or other, you are representing what is this. So now we come to the conclusion here, mathematical modeling, a representation of behavior of any device or any object in the form of mathematical equation. Mathematical modeling, now we come to the conclusion that mathematical modeling is the behavior of any device, any system put in the form of mathematical equation. Now, we want to know, what we want to know? how to make mathematical representation, how to validate them. If I make them, how do I validate them? Whether it is correct or not. How to use them. Then, under what limits I can use this. So before I discuss these things, let me go slightly beyond this one. Why do at all mathematical modeling? What the meaning is this? That is what we say, since the modeling of a device or a phenomena is essential for both engineers and the scientist. Any device or any phenomena, unless you model it, it cannot predict all types of behavior. So it is essential for both engineers and science people to know the mathematical model. Or out of the mathematical model, what I enjoy, see, just enjoy this. I go on playing with this mathematical model, I can enjoy it. Yes, I can do this also. I can do this also. What I imagined, beyond that I can do it. See and enjoy it, we also enjoy this mathematical model. Then we come to the point, what science says. Science tells you the principles. What engineering does, applies it. What is technology? Technology gives you a tool for these applications. So just as transistor was invented, what engineers did, took the transistor, put it in the form of different types of circuitry, whether for the amplification, whether for the switching, with all types of gadgets. Then technology came. How many transistors you can put in together to manufacture very, very complicated chip in the form they want. That is why we said engineers who are taking the inventions, applying it and using the technology as the tool are innovative. Now, to remain globally, what we are talking about the innovative, to remain globally competitive, what we must do and what we must understand is nothing but art of design. Unless I know the art of design, something happens, I will not be able to change it. So I must know art of design, then I must be able to modify whenever I need it. I must be able to modify it. If I know everything, then only I can modify it. So I must know the art of design. I must be able to modify it. The time comes, some modification I have to include. Yeah, this modification I will include. Then redesign it. Okay? How do we do it? These things, what we are just iterating. These things we are iterating. But how do we do it? This tells you a scientific approach to design. And what is this scientific approach to design is nothing but that mathematical modeling. So the mathematical modeling is a very powerful tool today. Anywhere you stand, whether you are mechanical, electrical, electronic, any engineering, it is a mathematical tool. You have to use the tool and then enjoy it. I design this one, I can go much beyond this. That is a necessity of the modeling. Is nothing but the nature, very nature of the technology advancement. One model say, I say SSI, small scale integrated medium scale integration, large scale integration, very large nano scale. Same model will not work in all. Modern refinement goes on as the technology advances. Modern refinement goes on. Otherwise, same model will not work. So the technology approaches its limits. Change in the fundamental aspect. That means the change in fundamental do not occur at the same pace. Imagine when the transistor was enormous. What happened? It was shocked and surprised both. Why so what? So small transistor will be able to so high, so thick, gigantic tube. Can it be replaced? It was just a surprise for them, and then shock for those who had very large inventory. Manufacturing process were on. What will we do in this one? But then it came into reality, and we accepted it. It is working very fine. It worked very fine. It is working very fine. So that is what we say. This with the advancement in technology. But we say change in technology. For us, I am talking about this environment of Indian university. Change in technology for us is more horizontal. Vertical, horizontal, you understand? Vertical is what? Coming from micro to nano to, say today, 22 nanometer, 16.5 nanometer. That is vertical. But so far we are concerned, it is horizontal. Changes are mostly transformation for us. We are talking about us. Changes for us are mostly transformation from analog world to digital world. You know what is digital world? It's known to you. Very robust against the environmental change, means against the noise. Very robust system. Digital system is very robust. So for the environmental change. So change is from analog world to digital world, or hardware to software. You understand this? Hardware to software. You are manufacturing a car. How many chassis you will produce? At what speed this whole car will not be overturned if suddenly the brake is applied? Then you have to go to software, design everything, test this one, so many iterations you do, and then ultimately you come to, yes, this should be the weight of the car, including everything. Then multi-chip to single chip. You do not know today, but we have seen multi-chip to single chip. There are number of chips. One chip output is connected to another chip, and then packaged together, only thing the input control and the output pins are available here. That is what is the connection inside it. You package yourself. Locally you have packaged it. That is what is the multi-chip. Then all aspects are computerized, whether it is production, whether it is design, all aspects are, because of the complexity, because of the fund crunch. So concept of engineering, when we talk about the concept of engineering, remains the same, but the modes of application changes. Say electronic filter. You know electronic filter. Somebody must be from the electronic branch here. Electronic filter. It remains the same. Whether it is T-type, whether it is pi-type, whether it is M-derived filter, everything, whatever you take, it remains the same. Only thing what it changed. It changed modes and applications. whether it was electronic filter, a passive electronic filter, or an active filter. So here, mode of electronics is passive to active. Passive, what we used in our day, we didn't have active filter, only passive filter. Bulky inductor, very large capacitor we used to use. That is passive. Very large dissipation of power, loss of signal, everything is there. But the philosophy is same, filtering philosophy is same. Only thing what we have done, we have changed from passive to active using operational amplifier. It became very handy, very cheap, takes very small space. That is what it changed from passive to active. Then finally it came to digital filter, IIR, FIR, finite impulse response, infinite impulse response filter. Now, having said so, we said to appreciate the effectiveness of mathematical modeling, what we must, how do we appreciate mathematical modeling? A, we must display some connectivity. We must tell you what is the connectivity or dependency of engineering on math and modeling. My concept of engineering is, if I know very good mathematics, if I know modeling, I am engineer. My concept. If I know modeling, modeling of device, modeling of circuit, modeling of system, anything I know, I am complete. Good mathematics and modeling. But from our scenario, this modeling is not present in your syllabi. In BTech syllabi, nowhere modeling is there. And complete engineering is only good modeling and mathematics, very good mathematics. When I am advocating good mathematician, what is the meaning of this? What does it do? Mathematics. Math helps to form the idea. Analyze what the information is there, analyze it. And then optimize it. That is what is mathematics. If you have good knowledge of mathematics, you can form very good imagination. Then math enhances ability to engage in what? Abstract thinking, and it erases imagination. Mathematical model, mathematical equation is there. What you can do? That's what I was telling. I enjoy playing with this mathematics. Meaning is this, go on imagining. This equation, what can it do? What more it can do? Go on imagining. That is what it is. So again, I reiterate, engineers are innovative and creative. What is creativity? Creativity comes from good imagination and abstract thinking. You must be creative. Having mathematics, very good knowledge of mathematics, creativity automatically. Then, innovative engineer must be equipped with very good substantial knowledge of math. So having said so, I am going to define this slightly. A study of a process or an object in one environment, if it is duplicated in another environment, Then he says, yes, your model is all right. Any process or any object you study in one environment, and if the same is duplicated in another environment, your model works well. I took this, a real picture. What it showed? It shows there is a cloud, then mountain having brownish color, then having trees. Now if I model it, in, I cannot bring so big things, I model it. Everything is represented here. And then said to the expert, gives it to the expert. Expert will tell, if this mountain brownish color, what is this ore? Can it be this ore? Bauxite? Can it be iron ore? It gives you too much information. Just a small miniaturization version of whole thing. Gives you so many information. So what engineers try to, from this information, what engineers try to gather as much as information as possible and then try to correlate them, these involved parameters, to foresee what can be here. Whether bauxite is there or ferric oxide is there. Electronic process, when we say, electronic process and objects are normally used as models. Why? What is the reason? Electronic process or objects are used as models. What is the reason behind? The reason behind is they are very complicated, unusual number of variables are there. Very complicated variables are there. And number of characteristics are there. Not one, many diverse characteristics. So we have to go for the model. Engineers must continuously improve method of mathematical modeling. One model I will come to, further I will come to them. One model cannot suffice. That way I told you, from very crude model to very refined one. Then we say SSI, then came to nano. The model cannot work. The one. So we must be able to refine it continuously. Right? How did you describe this mathematically? Whether partial differential equation or differential community differential equation. How do you define it? Go on defining depending upon your region. Numerical analysis, go on changing. Rangaputta method, I used to use very long day. Now you don't use. There are number of methods available here, or number of tools are available here, you can do it otherwise. Computer aided design can be said. Thus, modeling is the only effective approach to respond to the current need. What is the current need? Current need is crunch of funds, crunch of a space, crunch of time. How fast we can predict the behavior of the system, we can predict the behavior of the device. Alright? And everything, whether we structure, automobiles, graph, diagram, scattered plots, tree. Tree, you understand what is a tree? You are lost in a forest. Tree diagram tells you where you can go. And then the mathematical modeling is this, the mathematical modeling that you can reach there at this place. Then we say the model provides an insight into the physical system. When you devise a model, what it tells you? Device model, this is the device model, a small device model is there. It tells you, it goes inside into the device and tells you what is the behavior of the device, physical behavior of the device. Then different types of methods you can apply to find out finite difference method, boundary problem, or finite volume problem. All these things, that depends upon your experience, which one you apply, where you apply. These methods involve, so when we talk about these methods cannot be for the whole system. You have to split, say, if anybody is here sitting in from the background of electronics, even the characteristics of a diode, it can't write one equation. It is split into number of elements. Whole number of elements. That defines that this is the prediction of the behavior. This element, how it is predicting the behavior. Now this one, when we say mathematical modeling, all are under two categories known as black box and white box. What is the meaning of the black box is? You don't know anything. What is inside it? Nothing known to me. No parameter is known to me. I don't have any information about the system, what it is. I don't have anything known to me. That is complete blind. White box? Priori known to me. Yes, I know some priori. Many things is known to me. Then we say it is a white box or a clear box. But practically all are between these two. White box and none falls in this one, none falls in this one. It is practically in between these two. White box and black box. Mathematical modeling may assume different forms of depending upon the particular system, a system. It can be different. How do you take this? What are the parameters you have assumed? She has not assumed these parameters. Her mathematical modeling will be different than your mathematical modeling. There may be several different types of model of a device or any system. One may be very simple than the other. Other may be more accurate than the previous one. Another may be modeling DC voltage, DC current. Other may be model with AC voltage, AC currents. So model is entirely dependent upon your choice, which way you want to treat it. For example, an optical control model, which one is best? A, nothing but if you want to state a space analysis will be the best one. Transient response. Best one is transfer function model. For transient response, transfer function model is easiest. So that depends upon your experience, which model you are going to apply, when that depends upon you. Well then, these things may be described in terms of differential equation. These differential equations may not have exact solution. We have described it, but these differential equations may not have exact solution. Then what do you do? approximate. Go again back, approximate it. For example, we say, how do you do it? Newton's law of mechanical system or Kirchhoff's law. One is electrical, another one is. Anyone you can apply. That is known as simulation. You can apply it. And then a reasonable mathematical model is most important part of the entire analysis. Whatever analysis you are doing, you cannot say your analysis with the other model will be all right. No, it cannot be. Your approach is something different. Whatever parameters you assume, those parameters you are feeding into the analysis, those will give you different result than her model and her analysis. This only have shown. What do they say? Linear time invariant. What is this? Ain't nothing but transfer function model. How do you do it? Take the Laplace transform. Simple Laplace transform. Say differential equation of y the output, x the input, and we take it in the form of the Laplace transform. This gives you simplest equation. Simplified form of the models. One is known as material model. Material model we see here. Material, what is meaning of the material? A scale down there. Wind tunnel. What is the wind tunnel? To analyze the thrust of the rocket. Very long and huge cross section. Wind tunnel you have to construct and then see here. Because physically you can't see in the case of the rocket. So you have to generate here, simulate here. That is what is the material model. Then we said mathematical model. Mathematical model, you understand, we put in the form of the equations, symbols. Then we said logical model. Logical model, say if anybody has played with the microprocessor or microcontroller, the harmonium, unless you synthesize sa, the ray doesn't mean anything, sa re gamma. Even you try it, otherwise you will get nothing, no result in it. So that is why the logical. It depends upon this logic. Theoretical model. Directly I come to it. Theoretical model is a framework of ideas or concept from which we interpret the observation of experimental results. Check Newton's law of motion. You know, cricket ball. If you catch like this, you will be throwing it away. Every action has a reaction. Then you have to drag like this, then only you can catch the ball, otherwise the ball will drop. Right? That is what is this is theoretical model. You must take theoretical model in the form of the practice. That is what. Now coming to, which is known to everyone. See, this Dalton proposed the atomic model when 1800. And after 100 years, a gap of 100 years, another model was proposed. Means 100 years we were accepting this model. What was the model? Just see here. What is this model? Dalton model. How refinement came? Now I am coming to the refinement. How the refinement came? Dalton model, what was there? A complete solid. Dalton said it is a complete solid. It is indivisible, it is indestructible, but it has a shape, it has a weight, it occupies space. Meaning that it is a one complete solid, informed solid. That's what he predicted. And we silently accepted for 100 years. Then after 100 years, Thomson model came, refinement. What he said? Plum pudding model. That means, say this plum pudding is, the negatively charged are distributed over informed positive charge. Looking like plums are raising on the pudding. Means informally distributed positive charge and negative charge. It's not a complete one solid, but it has equal distribution of positive and negative charges. Then Rutherford came. What he said? Now divided into two parts. One is nucleus.
Excuse me, just a small announcement that after this lecture we will have one more expert lecture and then we will have lunch. Okay, so please bear with us for 10 minutes more. We will have one more lecture, then we will have lunch. Okay?
How much time? How much time? I will go ahead, no? So how much time? You tell me, man. How much time? I will take. Dense nucleus and negative cloud, electron cloud. That will be separated into two parts. One is the nucleus, another one is. Then came the board. Bohr model. What is it? Not only two parts. Electrons are present in the second part, but they are orbiting. They are not stationary, but they are orbiting. That is what the Bohr model says. What Bohr model tells you? Why I have taken this refinement? Coming to this point only. This refinement I have taken only to come to the point that I want to model the energy in different orbits of the atom. Different orbits of the atom. So if you take any one electron here, you can say centripetal force or centrifugal force. Electrons are at a distance from the nucleus, so it has a potential energy. Rotating, it has a kinetic energy. So total energy if you take into account and convert it, then it gives you 13.6 over n square. N is the principal quantum number. Nothing here. The last orbit gives you maximum energy, E3. Last orbit gives you maximum energy minus 1.5 electron volt. Nearest to the nucleus gives you minimum energy. That means any electron jumping from outer orbit to the inner orbit gives you light of quanta equal to h nu. Alright? Then Schrodinger tells you that yes, refinement is slightly more that it is in the cloud. They say this one. Can you see here? The cloud is moving. It's moving. That means quantum mechanical model. Schrodinger gave you the quantum mechanical model of the atom. Potential well, you analyze with this only. And I have to stop here because I am telling you. Violin is S. What is that? Integration, mathematics integration. What is integration? Summation bit by bit is the summation of integration. The integration number bit by bit summation. But if you are not interested, anything, I will stop here. Please, if you are interested, then only. Otherwise, what is the fun? Another lecture is there. You go for time constant RC, R and C. RC is the time constant. If time constant is 1T, how much I get? 63% of the output I get. So the time constant is very large, you go on and launching this time, what you get? The input is equal to the output. That means low pass filter, everything is coming. So now I will stop here. You ask me anything if you want, otherwise there are so many things I am going to tell me. You want to ask me anything? Sir, I will stop here.